Dear I'm really happy to see you again here and pleased to know you all are very fine and being healthy under this freaking COVID situation. Actually, this is the first time to me, first time to participate in the phrase in-person international conference for these 3 years. So that's why I'm really getting nervous. So, okay, the first position is, okay, so today I will talking about the experiment in JAA using the low energy ion beams. But the first position is, please forget about this type. Okay, so in this talk, first of all, I'm going to talking about the background of heavy element experiment and make a short review of our works using the ion beam and introduce our facility and apparatus shortly. And then let me share with you some of the data taken in the development of new ion source for super heavy element experiment. And then I mentioned the ongoing project at JAA. And then finally, I will make a brief summary. So, okay. The Christoph always mentions all the things about the periodic table, so I should say, here's our playground. So, I have to say and think this one. So, as Christoph mentions, in the heavy element region, the nuclear heavy element region, the chemical properties of the super heavy element might be changed because of the strong relativistic effect due to their large atomic number. Especially the theoretical calculations predicted that there is a violation of periodicity and here and here. They say the electron configuration. Okay, so electron configuration of the atoms might be changed. Differ from that's expected from the periodic table. Okay, so that's why we focused on these elements from the end of the action series to the beginning of the transaction series, the transaction elements, calling bridge elements. But unfortunately, so the person who calls these elements the bridge elements is only me. So please join me. Okay, so let me introduce our facility. Most of our work has been performed using this JAA tandem accelerator facility. And this accelerator is one of the largest electrostatics accelerator in the world. The range of the terminal energy voltage is from 2.5 to 18 megavolts. And this facility can provide the beam of various elements and the action type can be utilized. This photo shows our apparatus for the super heavy element chemistry, for the liquid chemistry and gas phase chemistry, and the online isotope separator. isotope. In this talk, I will be talking about this isotope system, And additionally, I'd like to say here, super heavy element chemistry in Japan started here about 30 years ago. So far, our group has studied the atomic and chemical properties of heavy actions using this isotope setup equipped with the gas jet transport system, equipped with a surface ion source coupled to the aerosol gas jet transport system. The nuclear reaction products produced in the reaction with the action target with heavy ion beams transported to the ion source by helium CDI2 aerosol gas transport system. In the ion source, the nuclear reaction products, surface ionized and extracted and accelerated to mass separation. In the ion source, the nuclear reaction products are surface ionized. In surface ionization, the ionization efficiency is related to temperature and work function of the surface and the ionization potential of the atom. By using this relationship, we conducted ionization potential measurement of heavy action elements. And as an application of this method, we performed observation of absorption behavior of the heavy accident. At lower temperature, apparent ionization efficiency would be affected with by the absorption enthalpy. So that's why these relationships can be used for this study. In this experiment, the ionization cavity here is used as the vacuum chromatographic current. So quickly, I will show you our experimental results. So here shows the result of the IP measurement of action series. The obtained values here, are here, and literature values are here. Our experimental results are pretty good agreement with the literature values, and this suggested that Lorentzian would have 7p half configurations. This configuration is different from the expected from the periodic table. And the ionization potential values are going up to nobly monotonically with atomic number. This suggests that 5F4 can filled up with electrons one by one. This means action series ends at Lorentzian. These works are published from Nature and injects. Okay. And another thing, as the application of the ionization potential measurement, we performed a vacuum chromatographic experiment of Lorentzian using this surface ions. Apparent ionization efficiency can be evaluated by Monte Carlo simulation, taking account of the adsorption enthalpy and ionization potential. By fitting the Monte Carlo simulation calculation to the data points, we obtained the adsorption enthalpy of the Lorentzian on the tantalum surface to be about 550 kJ per mole. This value is in good agreement with estimated value by semi-empirically and theoretically. So that's why we concluded Lorentzian would behave as the actional series, just like the rotation, as a homologous rotation. Okay, so based on these experimental results and experiences, we moved to the ion beam experiment of transactions. So, before starting the experiment, I have to mention the ionization potential of the transaction element. Here shows the trend of the ionization potentials with atomic number. The red and green dots correspond to the heavy actinide and transaction elements. This black line shows the limit of surface ionizable ionization potential. So, the element under this line can be ionized in surface ionization process. So, as you can see, most of transaction elements is not okay. So the surface ionization cannot be applicable for the transaction elements, as you can see. But in the case of Rutherfordium ionization potential is estimated to be about 4 electron volts. But you know, the Rutherfordium belongs to the group 4 elements, like zirconium and hafnium. So that's why the Rutherfordium could be a reflective metal. So then if you put the Rutherfordium to the ion source, Rutherfordium will lost on the surface by absorption. But the Rutherfordium have the volatile compounds, just like chloride and fluoride and so on. So if you use the volatile compounds as the ionization, we would have the super heavy element ion beam. But the estimated ionization potential of these compounds about 11 electron volts. So that's why surface ionization surface ionization method cannot be applicable. So then this motivated the new ion source for the transaction element experiment. Such as the electron bombardment. Bombardment is as ionization method. Okay. The motivation to enhance the research field of super heavy element study using ion beam at JAEA. We have started the development of new ion source for transaction elements coupled to the aerosol gaseous system. So, I mean, this type. And then, we have to think about the cooking after separation by isolate. We also started the development of the apparatus using low energy ion beam, such as gas cell curvature, and MARTOL, and trap for chemistry, and so on. Okay, so for this purpose, we employed EBGP as EBGP electron beam generated plasma method as an electron bombardment ionization, and have developed EBGP ion source. Here is a schematic diagram of the ion source. This ion source has the grid shape, the anode. This anode is covered with cathode. Okay, so you can see here. Anode is covered with cathode. The cathode is heated by the filament. Heated cathode. Okay, so thermal electrons comes out from the heated cathode inside to the element, the electrons enter to the anode. In this the anode, the nuclear reaction products injected into the anode. So then these products are ionized by heating by this electrons. Okay, so here IV ionization voltage is the difference of the voltage potential between the cathode and the anode. This is the acceleration potential of the electron to the anode. And IC ionization current is the current to get in the anode. This means the amount of electrons inside of these ions. Okay. In advance of the constructive of the ion source, we have simulated some component, some configuration of cathode and anode. Here shows some calculation results. And electrons comes out from the cathode, enter the anode, reach to the opposite side of the anode. The electrons, the bounce from at this side, by the difference of the electron potential. Okay, so on average, one electron passes through center 2.5 fission, about 1 or 2 times on average. Okay, so the picture shows of what the ion source system looks like. The EVGP ion source installed. The inside has also centered on this picture. So, okay, let me show you the typical mass spectrum of background, taking the background measurement. Okay, so the ions were observed in the entire range between from the low mass to the high mass, about 200. From ion source material, the tantalum and iron and nickel are observed, and as a background ion beam, nitrogen and oxygen and so on are detected. As a molecular ions, tantalum O and tantalum O2 result. So I can say that this ion source seems works as ion source. Okay, so then the next step, we introduce argon gas into the ion source directly via stainless tube, stainless capillary. So, in order to confirm electron beam ionized atoms injected into the ions. Here's the mass spectra obtained. As you can see, the argon, okay, so argon plus. Okay. As you can see, argon plus, argon 2 plus, and argon 3 plus ion beam are observed. And then we investigated the dependence of argon beam current on the IC, ionization current. Over the entire range of IC, 1 plus ion was measured. Where there's no IC when there's no IC, no argon gas, argon beam is observed. This means argon would not be ionized outside of the anode. Argon ion beam. Okay, argon ion beam current is increased monotonically with increasing ionization current. This means the more the number of electrons input into the anode, the more ion beam current will be obtained. And then, in order to find the optimum conditions for the ionization in this ion source, instead of argon gas, we introduced mixed gas. In this mixed gas, the helium, neon, and argon and krypton mixed with the same partial pressure. Okay. So here shows the change of the beam intensity of these elements as a function of ionization voltage IB. So as you can see, the beam intensity is increased with increasing ionization voltage. At some point, the beam intensity reaches to the saturation. And in addition, the heavier the element is, the more beam intensity is. So this suggested is. So, okay, here shows the ionization cross section for the noble gases. So this behavior corresponds to the change of this ionization cross sections. So this suggested that this EBGP ion source might be suitable for the super heavy elements, so the high Z atoms. Okay, so then it's time to the gas jet experiment. But let me get straight to the point. If we use the stainless capillary to introduce the gas jet, just like the Sato ion source, the ion source cannot work. It cannot work because the helium carrier gas injected the ion source too much to keep high vacuum for the ionization by electron bombardment. So that's why we employed aerodynamic lens. This aerodynamic lens is designed to focus the Earth's particle beams to 0.5 millimeter phi at the 3 centimeter away from this outlet. By combination of this aerodynamic lens with this 2 millimeter phi slit at the entrance, the vacuum improved and the ionization is the electron bombardment also this ion source can work. Okay, so here shows the picture of the aerodynamic lens. So, okay, the obtained mass spectra shown here. When helium CDI gas jet is injected in the ion source, the ion beams of cadmium and iodine were observed. They're clear. But in advance of the measurement, we determined the amount of CDI2 aerosols in the anode. By comparison to the beam current, we can rapidly estimate the ionization efficiency. Yeah, okay, I'll show you here. Yes, not so good. But we confirmed the EBGPO ion source works as the electron bombarding ion source so if we get some more improvement, I think that this EBGP is very good for the super heavy element experiment. I hope so. Okay. So let's talk about the cooking. At this moment, we can only use the surface ion source for the ion beam experiment. Sato aside measured the spontaneous fission properties of 258 fermium produced in the reaction of Einsteinium with oxygen. This is a preliminary experimental results, but in this study, it was suggested that there's a possibility of a coincidence of several fission modes in 258 fermium. I believe that in the near future he will give a talk about this in some conference, in other conference. Okay. Yeah. And in addition, we have been developing the MMR to perform the precise mass measurement at the end of isolate system. And this setup will be installed at the end of the J isolate beam line. Okay. Here shows the schematic diagram. We are going to the mass of the heavy action isotope after commissioning the near future. Furthermore, to expand super heavy element ion beam science at the JAEA, we are constructing a new isolate system, isolate 2. Last year. Okay. Also 1 year ago, we transferred the isolate component from the Takasaki Institute, the 200 kilometers away from our Tokai campus, to the tandem accelerator facility. Unfortunately, we can work. Unfortunately, we can work with only in the maintenance season of the tandem accelerator facility. But after 1 year, almost there. The commissioning will start in the upcoming summer. This is the next maintenance season of the tandem accelerator facility. And in parallel, we start to develop a new ionization technique, such as the laser ionization. Okay, the summary. To conduct studies using the super heavy element ion beam, a new EBGP type ion source coupled to the hand-seeded gaseous transport system have been developed. And EBGP ion source has been confirmed to ionize stable noble gas and high IP measurement, IP elements such as cadmium and iodine by electron bombardment. But there's a need to be improved. But I hope that in the future I can apply the BGP ion source to the super heavy element. And in addition, some apparatus using the super heavy element ion beam are under preparation, and another ISO system, ISO 2, has been constructed at JAEA. And the most important lecture of this talk is, in some cases, you should not trust the title of the talk. Okay. So here's the image of our future plan using related JAEA ISO. So thank you so much for your
Thank you, Tetsuya, for this nice overview of your recent work and the new projects. So we have time for questions. Yeah, please.
So very interesting talks. Just for me to understand, so in the previous talk, to get 5 events, we need, I mean, the people at JSI needs a month of experiments. How many what is the duration of typical experiments in this case where we are at lighter ions?
Typically, the production rate of the Rutherfordium is about 1 or 2 atoms per minute. So if the ionization resistance is 1%, we can get 1 ion per 1 or 2 hours. So then I think that this is not unrealistic value.
Okay, are there any further questions to Tetsuya? Yeah, there's one. This question.
So actually,
wait for the microphone, please.
yeah, this is very nice talk. So actually, you produced the Lawrencium 256.
Yeah.
So as I understand, the Lawrencium they are produced in the ionic form. So how they got neutralized in this your setup?
Sorry.
The Lawrencium they are produced by this fusion evaporation reaction in the ionic form.
Yeah.
So how they got neutralized there?
I didn't neutralize.
So then from where they are getting the electrons to get neutralized?
Yeah, okay, so the Lawrencium ions attached on the gas jet aerosols, the Lawrencium would be neutralized. And then that's it.
Okay, thank you.
And let's thank Tetsuya once again. We continue with the next talk. Now we will talk about spontaneous fission in super heavy elements.